Welcome everyone, and welcome to the AluVET Vocational Training and Education for the Aluminium sector. This training is co-funded by the Erasmus programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metals series of modules explains the simple theory of metals and of metallurgy to enable students in subsequent modules to understand aluminium, its alloys, how it is heat treated, and how it is rolled, extruded, and or welded. In this module, Liquid Metals and Solidification, we shall learn how and why metals melt, how they cool, how they alloy, how they solidify and form solid structures. This project is funded with support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. We will simplify and explain in basic terms all you will require to understand about the melting and solidification of metals, the solidification stages from liquid to solid. In this module, you will learn how and why metals melt, how different metals melt together to form alloys, how metals freeze from liquids to form solids, and what the structure of those solidified metals will comprise of. You will appreciate the feedstock structure, that is the starting stock, and alloying effects that you will encounter in the starting stock for both extrusion and rolling. So those are the logs that you start off when you extrude and rolled aluminium, the logs and the slabs. The understanding of how and why alloys form cast structures will explain in future modules on both the rolling and extrusion processes the need for homogenization. And we shall explain homogenization in those future modules. During fusion weldings, metals will solidify as miniature castings, and you will understand what the alloying effects will be and the resultant structure of these miniature castings within the welds. The basic knowledge of the solidification process will allow you to design defect-free welds. So let's start by considering liquid metals. When a metal is heated to high temperatures, the electrons of the atoms become highly energized. Consequently, the electron orbits grow wider, so the metals expand. At extremely high temperatures, the degree expansion is so great that the electron clouds, the metallic bond, cannot be shared amongst the atoms, and at this point the metallic bond breaks down. The failure of the metallic bond means that the metals melt and become liquid. In the liquid state, the atoms are held together only by weak forces of attraction. So a liquid lacks cohesion, so will flow and pour. So you need to understand that when a metal is melted, the metallic bond breaks down. That in a liquid, the atoms are held together only by weak forces of attraction, so the liquid can flow and pour. This means that in a liquid, atoms are randomly mixed together and are free to flow around. So if we add one or more different metal atoms together, they will mix together. So if we add two or more liquid metals together, we are creating an alloy. If we carry on heating the liquid metal to extremely high temperatures, the weak cohesive forces that hold the liquid together will break down, and then the metal will vaporize. So we have solid to liquid melting, and then liquid to gaseous vaporization stage. When metals are melted, the metallic bond is broken down, dissolved, forming liquids. We can melt two or more metals together into a liquid form. And we have some terms that we use. So when we melt two metals together, the lower volume of the metal, so the smaller amount of the metal, the lesser volume, we call that solute. And when we have a small amount, the small amount of metal is dissolved into the second metal, the higher volume. So we term the higher volume the solvent. So we have two terms. Solvent is the major or the greater volume of metal that dissolves the second metal, the second metal being a solute. Now, in our case, aluminium is always the greater metal, so it is the solvent. Think of it as sugar, the solvent, aluminium. Sorry. Think of it as sugar being the solute, being dissolved in water, the solvent, the aluminium. No two metals have exactly the same melting temperature, and different alloys will have different concentrations and amounts of solvent and solute metals. We can plot the melting of the two metals on a graph, which you can see on the slide. We plot temperature on the vertical axis and the concentration on the horizontal axis, the z-axis. Now you can see that the two metals A and B have different melting temperatures. On the left-hand side, we start with 100% solvent metal, that is aluminium, and there is no solute in it at this stage, so it is 100% aluminium, no solute, no alloying metals. And as we move to the right-hand side, towards the right, the amount of solute increases and the amount of solvent decreases. So on the right-hand side, we have 100% solute alloying metal, alloying atoms, and no aluminium. And in the middle, the two will be roughly in equal amounts. Virtually all metals are soluble in each other in liquid form. There are, however, limitations to alloying caused by temperature, where the melting point of one metal can be higher than the vaporization of a second metal. As an example, the melting temperature of tungsten is higher than the vaporization temperature of aluminium. Differences in specific weight can be so great that the two metals can separate into two distinct layers with a narrow boundary layer. For example, heavy iron and light aluminium. So apart from those two cases, we can mix metals together in a liquid form. We're going to look at solidification of metals now. So we start off with a casting temperature, perhaps 700–800 degrees C, significantly higher than the melting temperature of aluminium or of the alloy. As we start to decrease the temperature, the liquid cools down. Now, pure metals solidify at a constant temperature, a distinct freezing point, which is the same as their melting temperature. So we have a liquid metal, pure liquid metal aluminium. Its melting temperature is 660 degrees C. Now, as we cool the liquid metal down to its freezing temperature, 660 degrees C, it stops. Now, the pouring temperature, the casting temperature, has to be much higher than the melting temperature to ensure that everything has melted and to ensure that when we pour the liquid metal, it has sufficient superheat to flow into all the corners of the mold before it solidifies. During cooling from the pouring temperature, once the metal, pure aluminium has cooled to its melting temperature, there is a long pause. And you can see on the graph, freezing starts, freezing finishes. You can see that there is a big time delay at a constant temperature. And here, the temperature of the liquid is arrested at the constant temperature. And the liquid pure metal temperature remains constant at that temperature for some time before it starts to solidify. And the pause is caused by latent heat, the heat of melting, the heat energy being released and ejected during this constant temperature pouring process. Hence, we have a flat plateau. And latent heat is the energy required to change the state of a metal from solid to liquid. It's the heat that we have to put into a metal to change its state from solid to liquid, or the heat that we have to lose from liquid to solid. So during this plateau, this cooling plateau, the excess latent heat has to be lost. And once the latent heat is lost, then the metal will be all solid and the solidified aluminium cools from the freezing temperature down to room temperature. So on the graph, you have pouring temperature, liquid cooling, the freezing plateau, and then solid cooling.